everyone.
Hi.
Thanks for staying to the end. We're going to be telling you about how to secure Polkadot with 10 validators per parachain.
Yeah, we're Jeff and Al. I don't know what they've said.
Yeah.
We're researchers from the Web3 Foundation, and sort of our job is to make sure that Polkadot, which is this very practical protocol Gav mostly designed, actually works in theory. So this talk will be about the about the trade-off in between security and scalability.
Okay. All right. So we have. So I'm not sure how much familiarity people have with Polkadot. The idea is we want this kind of. We have all of these shards, these things we call parachains, and they're somewhat independent blockchains, but they are going to be depending on this relay chain for their finality, and it's called a relay chain because it relays messages between these shards.
So each of these parachains is like its own independent network, not only its own blockchain, but its own independent gossip network. And it's important for the scalability, like that not everyone has all this data, all the bandwidth passing through them, all the storage, all the computing power to verify each of these chains. And so we have to make sure that no individual actors have too much load, and in particular, like the validators in the relay chain play a key role in securing the shared security model and securing the parachains, and we need to make sure that they don't have too much data, bandwidth, etc., passing through them.
Okay.
So yeah.
You come up one at a time. Yeah. Okay. All right.
So returning to the title of the talk, the question sort of is about how many validators we had. We can try and compare with, say, sort of other network systems. So other protocols that are attempting multi-chain. So, for example, Cosmos are aiming for a sort of 100 validators per chain.
Maybe you probably need to click over to the next thing. Yeah, okay. All right, so, sorry, our slides were designed without the scrolling thing, but they somehow seem to be scrolling. And F2 wants to have around 300 to 1,000 validators per chain. Also, ultimately, part of the consequence of this is that their notion of validator is actually somewhat small. So in Cosmos, these validators can overlap, and in F2, they'll simply any 32F can be a validator.
Right. Yeah. So basically, there aren't a million. We don't know if we can get a million people. Maybe one day, but for now, they're not a million separate people to run these things. So it will be the case that there'll be people with 1,000 ETH, and they'll be basically running 30 validators. And yeah, so then the question is can we do this scalably? How much?
And there's a loss of independence here as well. I mean, if any 32F is a validator, then you have one machine running a lot of validators, and it's going to be pulling data from a lot of shards. And so then when we say, is this scalable, that's what we mean.
Yeah, so the question sort of is, for the scalability of this particular question, is like how many of these validator nodes for this kind of system can I run on one machine? And sort of the problems are, how much computation power? But I think probably slightly more important is the networking. So like the question is, how many peer-to-peer networks can I connect one machine to sort of securely? Like how many connections does that involve? How much bandwidth? It's just ultimately there is some bound. That validation is a limited resource. So we'd like to use it efficiently.
All right, so Polkadot is going to be a bit different. There will be sort of hundreds of validators, maybe hopefully soon thousands, and there will only be about 10 validators per parachain.
So we sort of promised that there would be 100 parachains sometime, not too long after launch, but we don't necessarily expect that we're going to have more than 1,000 validators, and this means that we have only 10.
Yeah, I mean, and I want to emphasize, there may be people running multiple validators, but when they do this, we want it to be a choice that they want to be dealing really with multiple, with, they can run a serious validator node, and the networking, they have some understanding of how much network it's actually going to be doing. Okay, but will this actually be secure? Can we actually make this secure?
I mean, Polkadot actually has, the MPOS has kind of some support for running multiple validator nodes and voting for sort of both of them, delegating to both of them, and you can get as many in as you have dots for. So we expect some Sybil here, but yeah, it's going to be much lighter than running 30 validators.
So one other, well, yeah, let's keep, okay.
So yeah, then so what do these validators do to secure a parachain? So the way Polkadot works is that we sort of divide each of these validators, divide our whole validator set into groups of 10 randomly, and we frequently shuffle these groups. And each of these guys will be parachain validators for this parachain, and their principal they'll be in the network for the parachain, and their principal job is when collators produce blocks, the parachain validators check that they're valid, sign them, will sign some header which goes onto the relay chain, which eventually means that this will happen in Polkadot. So we need these guys to check what the individual parachains are doing.
Okay, so, all right, so if we have the, it's still up there, that's fine. So, okay, so if we have these, 10 validators, we're expecting something like 5 to 7 signatures before this parachain block is considered something you want to include into a relay chain block. And, okay, so that's not a lot of people. It's perfectly imaginable that some malicious party could, just by luck, control all of them, or possibly with some manipulation, that the amount of luck they'd need would be reduced. Okay, so we want more checks.
So this is a few guys to coordinate. So one reason why, say, S2.0 have so many validators is because they wanted, if we choose them at random, that it's very, very, very unlikely that we have a majority of, bad validators. If we have a small section of bad validators, it's very unlikely that they end up on the same shard. But for us, we only have a few people to collude, and so you can always wait. If you have a small group, you can always wait until you're all on the same parachain and then try and attack it. So we need some backup here.
Okay, so we have these, we want some other parties to be checking these blocks other than just these parachain validators. So there's this word fisherman, which describes some of them, and we want them to be able to claim that a block's invalid, and that results in other people checking that it will be invalid, and if it's actually discovered eventually to be invalid, then the validators who signed off on it will be slashed.
And the fishermen themselves have some stake, and this allows us to sort of balance the economics. I kind of expect that if you're a full node, you can just add a flag to your command line or whatever to be a fisherman. And I kind of expect that majority of collators at least will be fishermen, as they have an interest in the validity of the network. So I don't think we're going to be too short of them. But there is a problem that makes this design hard to make working.
Yeah. So, all right. The block actually becomes sort of canonical. It can be finalized when there's some relay chain block including it.
Yeah. So this is the thing that's a bit different from, say, Bitcoin. So in Bitcoin, it's like you need to get the data out there because no one can build on you unless you tell them what the actual block is. And it's like selfish mining attacks. You hold it back for a bit, but unless you can actually 51% the network, you have 51% the hash power, you really want to, you want to be in the final chain, you've got to be releasing your blocks. But this kind of doesn't hold if your consensus is kind of subject to another chain. So it's the relay chain that determines whether this parachain block happened, and the relay chain only needs to see this signed header. This header signed by these parachain validators. So maybe no one but the collator and these parachain validators ever had the data in the first place.
Yeah, and these fishermen, whatever they are, they can't possibly validate a block that they can't see, and the validators can't know the other validators can't just know if this block's actually available for fishermen or whoever else to see, and just fundamentally, I mean, how do I know if some data exists if somebody will give me data unless I've actually downloaded it myself? So these claims of unavailability of if we are going to have some claims of unavailability, they're going to be subjective, and we don't really like this. We don't like that kind of.
Yeah, I mean, how do the validators know whether or not the Parachain network that they're not connected to ever saw this block? They don't.
Yeah. So I mean, a way to think about this. So imagine I have 1,000 friends, and I want to like convince them that I'm willing to give them some data if they ask me for it. So just to try and pull this away from the blockchain context for a second, I just want to convince them that there's some data they could get. So what do? Well, I could give it to all of them, but that requires sending the data 1,000 times. Another thing I could do is I can, and so this is there's another approach, however, and click.
Oh, right,
yeah.
Okay. So what we really want is like everyone, it's no good for having only a few people having this data, because they could be unreliable, disappear. What we really want is to rely on everyone, and the kind of.
So what I could do is I could give the data only to a few of them and have those small people vote, but that's not very good either, because I'm back in the same problem of only a small people doing it. So what I can do instead is I can take this data and I can erasure code it into 3 times as much data and give one little slice to everybody. And so now they can still do this vote, and if the majority, if more than a third, so 334 of these 1,000 people say they got their slice, then subject to them being honest, this means that the data could be reconstructed.
Right, and so we can kind of tie this in our particular. So in our particular system, it's the Parachain validators are going to hand out the data from this Parachain block to all the other validators, but it's only a little bit to each, so it scales. Not that much data to everyone. And what we're going to, and then we're going to rely on this for things like the consensus, for instance. So Grandpa is like a kind of Byzantine agreement thing. To finalize any block, it absolutely has to have 2/3 of people voting for it at some point. And if we introduce a rule saying people aren't going to vote for it if they don't have all the data for it, for each of the Parachain blocks in it, then under sort of the assumption that 2/3 are honest, then and around available, then if 2/3 of them signed it, then 1/3 of them will absolutely be able to give us this data, which means it's available. So in this scheme, we can't possibly finalize something that is in principle unavailable.
Right. And okay, so this so this gives us at this point we'll now see that you can sort of see that the amount of data we're actually handing out is only about 3 times the total amount of data that from this parachain, or the total amount of data seriously being considered for inclusion in the relay chain. So that's a hell of a lot less than the whole 1,000 or 10,000 validators times that.
Right, but in order to be actually sure that that these blocks are valid, it's not enough for them to be available, right? Sometimes we have to make sure that someone can actually going to check them. And because of the networking difficulty here, we actually need a protocol for that. And so the way it works is like this.
Okay. Well, so we have these fishermen who can report some invalidity. We have the correlators who can report. So correlators, the people from the parachains, they can sort of complain if they don't think a block is available, and then they're having trouble getting the full thing, which they need to build on. And of course, the correlators can act as fishermen as well. But those people aren't the highly staked validators. So we want something a little bit more from the highly staked validators, and so the key thing to think about here is that the validators assigned to the parachain is foreseeable by some adversary, but there's
right. Yeah. So the first thing is there's we can get a few extra validators to check. Like if more reports, more validate, more checks, and for these guys to check, they have to. They have to first talk to a Parachain validator, get the data. If that doesn't work because they're all bad, disappeared, then they talk to all the people and try to get hold of all its erasure coded pieces. And then they can check it. Now, of course, there were only a few Parachain guys, but what's like Parachain validators, and now we're only having a few people checking it. Why does this give us extra security? Well, so the problem with the Parachain validators is that everyone knows who they are. They're public entities, they attach to the network, and the collators need to know who they are. And so you can just, the bad guys can wait until the people doing the checking are all their friends before they launch the attack. So it's important for the random people doing the checking that no one knows who they are.
So the way we do this is there's a thing called a verifiable random function, which is quite useful. And what it gives you is it gives you some private randomness that you can prove was really this private randomness that you were supposed to generate. And so there's a few different schemes, but a simple one way to imagine it is that everybody generates a VRF, and it says which of the parachain blocks associated with this relay chain they're supposed to check. And we'd have some other things beyond that, but it means that now so we now will be sending more data around, but again it scales reasonably nicely in the number of parachains, and it's not at all foreseeable until the relay chain block has actually been sort of committed to and is being processed by Grandpa.
Right. Yeah. So the hope is here that we're going to catch this attack with high probability, and probably fairly fast, and hopefully this means we're not going to be able to. No one's going to be able to make money by attacking Polkadot, which should mean it never happens, because it's very difficult. I don't think it's very difficult for a bug to do this accidentally.
Yeah, and was a one
point here. So even if you're going to get caught, we're still only securing it by these few guys, and we're going to slash them when we catch them. But that might still be a relatively small amount of money compared to the things that are floating around in Polkadot. Now we're going to revert Polkadot, but maybe there's Polkadot's not going to be alone. Maybe there's something irreversible on the outside you can do, like convince the Bitcoin bridge to give you all the Bitcoin. And that might be more than these validators own. And so they could conceivably make money by that way. So so the way we're going to do this is we only want the outside world to act for large amounts of money, at least when we have finality on the blocks. So what we want to do is sort of delay finality a bit until we can do these checks. So we sort of want to wait for the fishermen and collators to give us these reports, maybe. And if any turn up, then we wait a little for all the extra checks. And only when we're happy with all this do we vote for this to be finalized. And the sort of result of that is that we don't finalize a block unless with good probability it's valid and available. And yeah, so sort of what that means is it's going to be expensive. The expected cost of attacking Polkadot and actually getting a finalized block in is going to be quite expensive. We can make it sort of comparable to the amount of stake in the whole system, which means that if you have a chance of being able to get away with it, but it's going to be cheaper on average to just buy a third of the staking dots and attack the relay chain than it is to be able to attack the parachains this way. And so that's sort of the security guarantee we get.
And so we have one more caveat about this. That's next page. So there's one more caveat about this about this design. Most of these blockchain networks just work on a bunch of gossip protocols, and the thing we've just laid out is not very gossip friendly, because it involves, when we do this erasure coding, it involves sending these distinct erasure coded chunks, which will all be distinct, to each individual validator. So you need basically a point-to-point protocol of some sort, and if the thing gets too large, then you need some kind of routing scheme.
So yeah, there's some fun here. We can't basically, this is all the data. This is what we wanted to avoid giving to everyone. But once this is kind of fixed, then this is sort of how we can, provided there are enough honest people watching every chain, we should be able to get away with much fewer validators and therefore more scaling.
Yeah. And just another comment here, as we're going through and thinking more about the networking, we're finding other places where probably we shouldn't be using gossip, and then we're also finding places in gossip where we now are understanding a bit more why certain things should be done with gossip. So this has generally been the sort of turning our attention more towards networking has been generally useful here.
So I'm not sure anyone really knows how to do networking in the multi-chain context yet. I want to see what other projects. What other solutions other projects come up with. But this is kind of what we're thinking. But if we get this sorted, then Polkadot will be reasonably secure. Yeah, any questions? I suppose we've got time, right?